So the problem we had with the standard Dijkstra algorithm was that we ended up going in the wrong direction a lot. If we look at this very simple network, we want to go from alpha to omega here, and we want to just go straight over there. That will be the simplest route. There's not many choices to make here. But when we start analyzing this, we use our simple rule. We say, what's the shortest step I can make? Well, the shortest step I can make is actually to go to B, because 3 is greater than 1. So this is shorter over here. Now, it's still shorter to carry on going that way because our cost of getting to there is only 2, which is less than 3, which is what it would cost to go there. Okay, so now we've gone down here, and that's going to cost us 3 to get there. So maybe that's okay. So then we go back here, look here. Well, it's already cost us another 3 to get to there. That's 6. So now we start looking here again because 6 is greater than 3. So now we go to here. That costs us 4 to get to there. You see where we're going with this, entirely the wrong direction. We've gone entirely the wrong way simply because we have to follow the least cost first before we can continue in the right direction. It's very obvious which direction we want to go in, but the computer couldn't see that from the data it was given. So what we need to do is to give it some more information. So here we come to the A-star algorithm, which uses the Dijkstra as its foundation, but we add some extra bits to it. So this is the same network as before, where these black numbers are the cost distance. There's some sort of cost weight. They're not related to the actual distance. But then we can add in, using red numbers, the straight line distance to the target. So here is our target, and it's 0 meters away from itself, because it is itself. So the distance to omega is 0 at omega. The distance from alpha is 14. The scale in this should be relatively okay. I measured it with a ruler on the screen. Brilliant. It's absolutely not a recommended way of making a map, but this is how I did it. So we have a distance of 14 when we go from there to there, but actually we want to go in the other direction. But the distance of alpha from omega is 14. And similarly, the distance to A is 13. And we can calculate the distance for all of these others, so that we say this is the straight line distance from the node to the target, from each node to the target, which is omega down here. So that's some extra information that we are giving our algorithm to work with. We are still constrained to traveling along the network. We can't just follow the straight line. We still have to travel through the network, but we are giving it an extra clue here as to where we want to go. So what do? Well, we do a similar setup as before. We start with alpha, look at the card, but now our cards are a bit larger and they have an extra square on them. So we still have this from node. Where were we previously? How do we get to alpha? Here is the node we're interested in. How do we get there? Well, we started here, so there is nowhere. The weight is 0. We haven't had to pay anything to get there, but the distance was 14, and the weight plus distance sums to 14. When we now look at these cards, we can see that if we do our first calculation, the distance to A here is 13. So 13 plus 4 is 17. So we add these two together. So when we look at B, we get a cost of 1 and a distance of 10. So that has sums to 11. And C here, which is the other one we can see from alpha, that sums to 15 because the cost is 3 and the distance is 12. So now we need to reorder those, so that they reorder them by this last column here. So they look like this. They come in this order, 11, 15, 17, and we move B up because that's the next one of any interest, because it's the lowest total cost, as it were. From B, we can see F and we can see A. And A, we're going to adjust the cost of that in a minute. At the moment, it still costs 17 to get there. Here comes F into the image, and we adjust the costs. In order to get to A now, it costs 16 because we've adjusted the cost of traveling through the network, but the distance is still the same. F is entered into our calculation here with a cost of 4, that's 1 there and 3 there, plus the 6 is the total distance, so it's 10, that sums to 10 here. And when we look at this, actually that 10 is the lowest we've got in our cards of choice here. So we move that up, it comes to the top of the pile, and it ends up being the one we're examining, so we're down there. When we look at this, what can we see from F? We can see omega, we can see H. Right, okay, so we calculate the costs for those, and it's going to cost us 7 because there's no distance cost associated with omega, whereas H is going to cost us 12 because we have the cost of traveling through the network, which is 5, plus its distance loop, which is 7. So we then move omega up to the top of the list, and we're done. That was much, much quicker because we added this extra information. So now, in this case, we could tell the algorithm that we want it to go in a particular direction. This is the preferred direction. This, in actual fact, when we were doing an examination of other types of network, it doesn't have to be this Euclidean distance, the straight line distance. It could be some other piece of information that we can share with the algorithm to speed things up. What that might be depends on what it is we're investigating. But in this case, for us, when we're doing these networks, that straight line distance is the extra information we want to speed our search up through the network. No diversions at all.